All right, so section 3.3, we're going to move into multiplication and division. Today we'll do multiplication specifically, and then the next lesson will be about division. So to start with, we're going to talk about what is multiplication. So if we have finite sets A and B, where the number of items in set A is A, and the number of items in set B is B, then if n does not equal 0, then n times A equals A plus A plus A plus A n times. If n does equal 0, then we say that 0 times A is equal to 0. And A times B is equal to the Cartesian product that we had seen before, A cross B and the number of items in that set. We saw that happen back in chapter 2. I think it was about 2.2. All right, so what I'm going to show you next is 3 models for multiplication. So we did models for addition, and I think we had 3 or 4 of them. Now I can't remember. I think there were 4. And then we had models for the subtraction, the same kind of models for subtraction. We're going to do 3 models for multiplication. So here's our first one. It's the repeated addition model. This, again, it kind of starts out with how most people would describe what is multiplication. Well, it means adding something together the same number, a bunch of numbers of times. So this one goes with that idea. Giselle takes 3 tests every Friday. After 4 Fridays, how many tests has she taken? So the idea behind this, of course, is that we have 3 times 4. I mean, that's what we're going to want to do is 3 times 4. But this says that we've got 3 tests every Friday. So if we were thinking of this in terms of addition, it looks like we're adding 3 together every time. Okay? Something that recurs over and over and over again. Right? Like if I go out and I run 3 miles every Tuesday, Wednesday, and Thursday, how many miles have I run after 3 weeks? That kind of a question. Something where it's the same number every single time happening over a course of time. I guess we should give the answer as 12. So this one would be 12 tests. Now, array model, and this is used specifically for sets, and it is important here, so underline that if you need to. It's used for sets. Minyu is baking cookies. He's able to place the dough 3 cookies wide and 6 cookies long in his pan. How many cookies will his pan hold? Now again, the nuts and bolts of this are that at some point we would like our kids to recognize that this is just 3 times 6, right? It was 6, wasn't it? Yeah. So it's 18 cookies. But visually, as soon as I said cookies on a pan, there was probably a mental image that came to you, correct? You've done this before. You've seen this before. It looks like something familiar. So you probably had an image that looked something like this. This is called an array. Okay, an array is where the length and the width may be different, but you've got the same number of objects all the way across in rows and columns. This is 3 by 6. And of course we end up with 18 cookies. But when I talked about tests happening, 3 tests every Friday, there is no way you thought of this kind of picture, did you? You didn't. Right? This image did not come to mind. All right, one more. It's called an area model. This is used for measurement, again, specifically for measurement. If you remember, sets are whole objects. A cookie is a whole object. Measurement is something where we've actually measured length or width or time, something like that, okay? It can be broken down into decimals as measurement. Alexis is planning a garden. She has a space that is 5 feet wide and 7 feet long. How much area does she have in which to plant? So we are 5 feet by 7 feet. We recognize, of course, that that's multiplication. We should be getting an answer of 35. Do you know what the units are? Square feet. Square feet, which is how we write it like this. But the image that you have in mind hopefully looks like a rectangle. And the rectangle is a 5 by 7 rectangle. So now I'm not going to promise that mine is going to look actually legitimately like equal plots of land, but just pretend that it does. It looks like a grid of some sort. We're going to give it a shot. Okay, well that certainly could have gone worse. And again, these should all look like little squares at this point, but they're not going to. That might be one of the best ones ever that I've done, and you all were here to witness it. All right, so this is 7 by 5. I mean, we could like count all my boxes, right? You don't even necessarily have to draw the grid in when you're doing a problem if you were doing it this way. But we do have a rectangle in our mind when we created this particular garden. All right? So, this is now audience participation time. Turn to your partners. Again, you don't have to create the answer. Not that the answers are hard, but that's not the expectation. The expectation is to create 3 different problems with this perspective in mind. One that's repeated addition, one that's for an array, and one that's for area. All right, we need some volunteers. Somebody tell me what you did for your repeated addition model. Abigail?
We put Ryan has 2 basketball games a week. After 4 weeks, how many basketball games does he have?
Fabulous. Another example of repeated addition. Taryn?
Josh drives 5 miles to work every Saturday. After 5 Saturdays, how many miles does Josh go?
Very nice. Miles to work. All right, what's next? Another, let's do an array one. 2 array, or we'll do 3 models for arrays. Go ahead, Sam.
Mrs. Smith is setting up the classroom. She sets the desks, 7 desks across and 7 in each row. How many desks are in your classroom?
Very nice. So desks in a classroom, that often occurs in rows. That makes sense. Did you guys want to do one? Emily?
I put Chloe is making pizza rolls and we can only place 5 long or 5 half-baked pizza rolls with Chloe half.
Pizza rolls. You know, I do that for my son for lunch, and he's got a little container we put them in, and exactly, we got to do the rows and the columns in there and figure out how many he can take. All right, one more example for an array.
Teacher sets up her classroom with 4 desks across and 6 desks in each row. How many desks does she have in her class?
It's almost like you guys are going to be teachers or something, right? Yeah, very good. How about some area models? There should be 2 groups who haven't spoken. Okay.
I said Hannah's building a pen for her dogs and is 12 feet long and 3 feet wide. How much area did her dog have?
Excellent. Pen for dogs. Who else hasn't spoken? All right.
You're fencing in your new puppy. The space you have is 4 feet wide by 6 feet long. How much space does your
Kind of
puppy
like
have?
the animal lovers too, don't we? All right, fantastic. I always like to talk just a little bit more about array because there's so many things that come in arrays, and you guys mentioned the classroom, desks in a classroom, which is great. Can you think of other products that you think of in arrays?
Grocery stores.
Grocery stores, the aisles in a grocery store.
Kind of, maybe.
Well, they're set up in rows, but I don't know that you necessarily have. You could talk about like shelves or something like that in a grocery store. You could. Any other thoughts?
Eggs.
Eggs. You know what? I was just thinking about eggs, and I've never even mentioned eggs in class before, so that's kind of crazy. Eggs. That one works. Yeah. So like the spaces on a calendar. You could do spaces on a calendar, especially if you've got one that's sort of the same number of days of the week and the weeks right on the same calendar page, like think February, because that's a nice 28 number. What about shoes?
You put your shoes in rows,
Okay, yep, that would work.
maybe theaters, like the seats.
The seats in a theater, definitely. Also thinking about like toilet paper rolls or soda cans. Those also occur that way.
Parking lots.
Yeah, parking lots would be a good example. So we have lots of things that occur in these different sort of visual imageries for us. We're going to move next into whole number properties for multiplication specifically. We've done these for addition. We found out that like nothing held for subtraction. And we're going to take a look at which ones hold for multiplication. So our first whole number property is closure. If you remember, closure is the idea that when I take two elements of the set and I combine them with the operation, I get another element of the set. It worked for whole numbers and addition. We talked about how it didn't work for whole numbers and subtraction. It worked for even numbers and addition, but it didn't work for odd numbers and addition. So it works for multiplication as well. If I take two whole numbers and I multiply them, I get another whole number. So think with me, what happens if I take two even numbers and I multiply them? Does it work? Yeah, it works. Even times an even is another even number. So the even numbers were closed under addition, and they're also closed under multiplication. What if I do odd numbers? You get an odd number. Do you always get an odd number with multiplication? Odd times odd? You do, actually. You do. And the reason that you do is because the only thing that makes an even number is having a factor of 2 in it. Right? The reason that 18 is even is because it divides by 2. Well, if no odd number divides by 2, and you multiply two numbers that don't divide by 2, they never divide by 2 either. So odd numbers are actually closed under multiplication, but they weren't closed under addition. Okay? So multiplication has some different features than addition does, and they do work for closure of whole numbers. The commutative property is the next one. The commutative property, of course, says that the multiplication in any order is going to be the same. So 7 times 3 is the same as 3 times 7. And I mentioned this in passing last time that we talked about for addition as well, is that this is why multiplication tables build upon themselves very nicely. If you're working from the 2's tables up, eventually when you get to the 8's, right, 8 times 7 and 8 times 6 and 8 times 5, you know all of them because you already did them in a lower multiplication table. So you only have the new ones, 8 times 8, 8 times 9, and above that. All right, the next one is the associative property. The associative property is for all whole numbers, A, B, and C. The order of the multiplication doesn't matter. So A times B times C is the same as the A, and then we group the B and the C together. We had an identity property for addition. What was the identity element? What was its value? It was 0, right? 0 is this number that we can add to things and it doesn't change anything. But we have an identity element for multiplication as well. The identity property says there is a unique number, 1. That 1 is called the identity element, such that for every number, when I multiply it by 1, I get the same value. So A times 1 is equal to 1 times A is equal to the same value A. The 0 property. Now the 0 property says that when I multiply by 0, again, kind of like the identity property, on either side of the number, so A times 0 or 0 times A, I still get back 0. I don't get back A. That's the identity property with the number 1, but I get back 0. And we have a property now that combines two operations together. It's called the distributive property. So this distributive property works with multiplication and addition or multiplication and subtraction. And it says that if we have A times the quantity B plus C, it is equal to the same thing as AB plus AC. And plus is not special, we could do it with minus. We do a subtraction. Okay, so just like we did with addition when we first introduced these properties, I'd like for you to take a look at 6 properties, or 6 examples, and identify the property. first do it your own, all right? And then I'd like for you to compare in your group and see if you have the same thing. If you and somebody in your group differ, talk about it and see if you can figure out which one it should be, and get that, you know, agreement among yourselves.
The second parentheses. Did you do E outside of the first? Or just add it? I don't know. Yeah. I mean, I can see how it works. How you could distribute because you like times 4 by the first parentheses, and then you have another set that does the same. Like I see how.
All right, let's make sure that everybody's on the same page now between our groups. I hear a lot of good stuff. So what did you guys decide the first one was on part A?
0.
Good, that's the 0 property. How about the second one? That's commutative. It's easy to look at that one and think it might be associative just because you see commutative. Because you see parentheses, but you have to be careful of where you see the parentheses. It's actually around the same set of numbers. The numbers are just in a different order. Whereas if you compare that to the part on number C, or the third one, what is that one? Associative. That one's associative. So the parentheses actually have different numbers in them, but the numbers are in the same order, 7, 3, 4 on both sides. What's D? Identity. And we mentioned this before when we did the additive identity. The identity is different depending on if you're talking about addition or multiplication. So on this one, you don't have to do this for associative and commutative, but on this one you need to identify that this is the multiplicative identity. So if you didn't write multiplicative down there, go back and add that in. Because the multiplicative identity element is different than the additive identity element. What did we think E was? That is the distributive property. So if you're taking a look here, this 5 gets distributed to the 3 and to the 4. So this is the distributive property. All right, so F looks a little weird, right? Yeah, it does. It looks a little weird. So what property do you see there or think you maybe see there? It is distributive. Good job. So what they've done is they've taken this entire thing and they've distributed it to the 3 and distributed it to the 4. So you see the 1 plus 2 times 3, 1 plus 2 times 4. So this is a distributive property as well.
For E and F, do we have to like say whether it's distributive addition, distributive subtraction?
No, because they work exactly the same way. It's kind of like saying, do I need to say commutative addition or commutative subtraction? No, you don't have to on those. The only reason we do that with the multiplicative identity and the additive identity is because they refer to different numbers specifically. All right, before I stop this video today, this is the natural stopping spot because we're moving into division next. The reason I'm going to keep this recording is because I want to make sure that the 2 folks that we have that are missing today, if they watch this video, recognize that they're going to watch another one because you are too. You guys are my only class that's not caught up from our snow day, all right? And we're going to catch up this weekend so we don't have to catch up over spring break. Can I get an amen? Yeah. Yeah, you don't want to have to do extra work on spring break. I don't want you to have to do extra work on spring break. So I'm going to let you watch the division video. It's already been recorded from a previous semester. If I'm guessing, it's probably 20 minutes. It shouldn't be a very long one, okay? So there's a division video. And then the homework for this will be due on Monday. Okay, homework from section 3.3. Now the good news for that as well is that there's no homework to do over spring break. So that's going to be good, right? Since we go ahead and get caught up now, okay? So that's what's going to go on.